So now we're going to see a bunch of examples of normal form games. Specifically, they're all going to be 2x2 by matrix games, which is to say there's two players and both players have two moves. You can get quite a lot of mileage out of just those examples. So the first example is called either matching pennies or penalty shootout, depending on the story that you tell. So typically examples in game theory come with a kind of story, and the story is not extremely important. It just makes it a bit more memorable. Importantly, the game can be applied in situations where the story does not apply. So this is the two-move version of rock paper scissors. So instead of having three choices, you have two choices, which means then you don't have to worry about ties. So matching pennies is a game where two players simultaneously call out either heads or tails, and if they call out the same thing, then player one wins and gets the coin, and if they call different things, then player two wins and gets the coin. So this is a situation where player one would like to coordinate with player two, and player two would like to differentiate from player one. So this has a payoff matrix like this. On the main diagonal, these are the same. So player one gets +1, player two gets -1, and on the anti-diagonal, they say different things. So player one gets -1, player two gets +1. A different but more intuitive story you can tell about this is it's a penalty shootout, where player one is the goalie and player two is the penalty taker, and we simplify this to the point where the goalie dives left or right, the kicker kicks left or right. So the goalie would like to coordinate. The goalie would like to dive in the same direction that the kicker kicks. The kicker would like to kick in the opposite direction to the goalie dives. Okay, and this, like the same as rock paper scissors in the previous video, this is an example of what's called a zero-sum game, which is for each of these outcomes, for every combination of moves, the sum of all of the payoffs for all players is 0. So zero-sum game is what it sounds like. Payoff sum to 0 always. So this is a special property. So this is usually not the case. So zero-sum games are something like games of pure conflict. So it's like for one player to do better, somebody else has to do correspondingly worse. Okay, so now we come to the most famous example in game theory, which is the prisoner's dilemma. So the story here is that the two players are prisoners who are being held in different cells, and the police question them and try to get each of them to inform against the other one. And depending on how much information the police get, they could get higher or lower prison sentences. So each of the players has two choices. They can do what's conventionally called cooperate, which is keep omerta, which is the mafia vow of silence, so say nothing to the police, or they could defect, which is to rat on the other one. This is kind of unnecessarily confusing because defect is cooperating with the police. Cooperating is cooperating with your fellow prisoner. And we have a very particular setup of payoffs like this. So if both of them stay silent, then both of them get low sentences. So here, payoffs higher is better. So we think of low payoff as getting like a long prison sentence, and high payoff. So the highest payoff here is 3, which is you get let off. So here, if player one stays silent and player two rats on them, then player two gets the longest possible sentence, which is 3, and player one gets let off, which is 0. Sorry, this is the wrong way around. Player one stays silent, so player one gets the longest possible sentence, which is 0. Player two rats and gets let off, which is a payoff of 3. And correspondingly the other way around. If both of them stay silent, then they get a very short sentence. So this is less good than being let off. And if both of them rat on each other, then they get a longer sentence, but not as long as if they'd stayed silent. So this is a very particular set of payoffs, which makes this game have some kind of counterintuitive properties, which is what makes it famous. So we'll be seeing more of this game in the next couple of weeks. So notice, so we can kind of intuitively think about this. Both players would like to stay silent. So that is to say, both staying silent is better than both ratting for both of them. So both of them prefer to be here than to be here. But if you're here, then both players individually would like to rat on the other, because then they get let off, which makes this a kind of unstable thing. And being so, if you're the one who stays silent when the other one rats on you, then you're the sucker. So this is the worst possible payoff. One reason that this is important is that this is a basic model of what's called a social dilemma. And these things are just absolutely ubiquitous in economics. So a random example, nothing to do with anything at all that's relevant to society, is cooperate is kind of like cutting carbon emissions. Say if you're a country or a big corporation, and defecting is like business as usual. So everybody mutually benefits from cutting carbon emissions, but as long as at least one other person is not cutting carbon emissions, then you would privately like to raise carbon emissions to allow you to like produce more of your product or whatever. Okay, so here's an example which is a kind of mixture of cooperation and conflict. This is traditionally called Battle of the Sexes. Errol Rubinstein gives it the alternative name Barkov-Stravinsky, which conveniently has the same acronym. So we have two players where each of them can independently choose to go to a Bach concert or Stravinsky concert, and the players have lexicographic preferences, which means they have a kind of first priority that they would like to be in the same place. And given that player one prefers Bach and player two prefers Stravinsky. So here, so we have two coordinating payoffs where, so here and here they go in the same places, and if they both go to Bach, then player one gets a slightly higher payoff. If they go to Stravinsky, then player two gets a slightly higher payoff. And then along the anti-diagonal, they're in different places, so they're both unhappy. In this one, they're both alone in their favorite place, and then this is the worst possible thing where both of them go alone to their less favorite thing. There's a variant of this which is actually a bit more common, which is traditionally called Meeting in New York, which is a purely cooperative version, which is symmetrical. So that's the no conflict version, where neither player has preferences over where they go. They only care about being in the same place. So I'll probably set an exercise or two on that game instead of showing you in the slides. Okay, here's another interesting example. It's called the Stag Hunt. So both players can choose to hunt stag or hunt hares, where the idea here is that hunting stags is difficult and will only be successful if both players commit to it. But if you hunt hares, then you would prefer the other player to not hunt hares, because then you get all the hares. Whereas if both players hunt hares, they have to share the hares. So here, for example, player one has tried to hunt the stag and has failed because player two is not helping. Player two is getting all the hares. So this kind of thing. So here is an example of this. When I first taught game theory, the negotiations between UK and the EU27 were still going on, and I wrote that this was a kind of simple model of the domestic politics of the negotiation, where hunting stag is to try to get the deal. So it kind of works if it's the best possible outcome for everyone, if everybody commits to it, and then hare is try to sabotage the deal. Anyway. Here's a last example. So Chicken is a game played by two gangsters who drive straight towards each other along a long straight road. So if you are the first one to swerve, then you're the chicken and you live in disgrace. And if neither player swerves, then you both die. So here, both players swerve simultaneously at the last possible moment. So that's a kind of neutral payoff. Here, player one swerves first. Player two goes in a straight line, never swerves. So now player one is in social disgrace, gets -1. Player two has won. But if you both go straight, then you both get some negative payoff. So you both crash and die. So this is a model of, for example, nuclear brinkmanship. So you can so this is everyone dies in nuclear apocalypse. And then the +1 is like you look strong domestically by not backing down.